Hello everyone, today we will walk through a fundamental MATLAB script designed for communication systems, covering signal generation, frequency analysis, and noise simulation. We start by clearing the workspace environment to ensure no legacy variables interfere. In tasks 1 and 2, we define our base signal parameters, an amplitude of 5, a target frequency of 2 kHz, and a high sampling frequency of 100 kHz to guarantee smooth data visualization. We then define a time vector from 0 to 1 millisecond and generate our first continuous time sinusoidal wave using the equation x1 equals to a1 multiplied by sim 2 pi ft. To visualize this generated signal, we look at this part. The top subplot shows the continuous time representation of our 2 kHz sine wave plotted using MATLAB standard function. It yields a clean perfect wave with a peak amplitude of 5. Directly below it, we use the function to see the discrete time representation. This format highlights the individual sample points gathered across the 1 millisecond duration, giving us a clear view of how the analog wave translates to digital data points. Next, in task 3, we shift from the time domain to the frequency domain using the fast Fourier transform, or FFT. After computing the two-sided spectrum, we convert it to a single-sided magnitude spectrum and scale it properly to accurately reflect the true amplitude. As visualized in figure 2, the frequency axis is zoomed into the lower frequencies, from 0 to 10 kHz. As expected, we see a single sharp dominant spike exactly at 2 kHz with a magnitude of 5. Perfectly matching our original signal parameters. In task 4, we introduce complexity by generating a second signal, x2, which has an amplitude of 3 and a higher frequency of 5 kHz. We combine these two signals by superposition, calculating x combined equals to x1 plus x2. Looking at figure 3, the top subplot shows the resulting time domain wave. It's no longer a simple sine wave. It's a more intricate composite waveform due to constructive and destructive interference. However, looking at the time domain alone makes it hard to decouple the individual components. By running another FFT and moving the bottom subplot, the frequency spectrum beautifully isolates both components. One peak at 2 kHz with an amplitude of 5, and a second peak of 5 kHz with an amplitude of 3. Finally, in task 5, we test the resilience of our communication system by adding additive white Gaussian noise using the AWGN function under two scenarios. A high signal-to-noise ratio of 20 decibels, representing a relatively clean channel, and a low SNR of 3 dB, representing a highly degraded channel. Figure 4 gives us a comprehensive comparative look. In the top left, the 20 decibel time domain signal shows minor fuzziness, and its corresponding spectrum on the right easily identifies our clear peaks at 2 kHz and 5 kHz over a very low noise floor. In contrast, look at the bottom left plot for the 3 decibel signal. The time domain wave is heavily distorted and looks like chaotic noise. Yet, thanks to the power of the Fourier transform shown on the bottom right spectrum, we can still clearly distinguish our signal 2 kHz and 5 kHz signal spikes rising above the elevated noise floor. This completes our walkthrough, demonstrating how MATLAB serves as an invaluable tool for analyzing and troubleshooting communication signals in both clean and noisy environments. Thank you.